Okay, so there's some issues with the modern theory of polarization that have bothered me for maybe since the beginning, and I always attributed this to my inferior ability to understand things rather than anything serious. And maybe I've gotten a little braver as I got older, or maybe I've gone crazy. So David Vanderbilt thinks it might be the latter, so he suggested that maybe they needed to do an intervention, or maybe I've gone over to the dark side. But I've been trying to convince the masters of this field, David and Raffaella, to actually maybe even co-author this paper with me if I ever manage to write it up. And they've managed to correct many of my misconceptions that really were misconceptions, but I still think there's a few issues. So I'm at the Carnegie Institution, and we used to be called the Geophysical Laboratory, but the Geophysical Laboratory doesn't exist anymore. We've been reorganized. So anyway, I'm at the Carnegie Institution for Science, and I'll just, in Washington, and you can see it's sometimes a little nicer here than it is this time of year, but actually it's not bad. You know, when we were in Tampa last year, we had wintry mix, you know, so this isn't bad out here for Washington for this time of year. So I'm coming from a different direction, always I was, and maybe that's part of the reason that I have some different feelings about things. By the way, this book of David's, you've got to buy one. I mean, it's really a great book. So, so I'm going to argue about, it is your book, right? I'm going to argue about a few things in here, but basically it's, like I said, it could be my problem. So I'm coming at things from a thermodynamic perspective, and I meant to turn on my timer. And that's maybe part of the difference. So I think of polarization as being part of the free energy, and as opposed to being say electrostatic, electrodynamic physical variable, just where does it fit in terms of the free energy? And it's defined really as the derivative of the free energy density with spectric electric field. That's what I think it is. And this goes back, by the way, even papers by Raffaella and David say the same thing. And if you look at Nye's book, he goes into great detail in the thermodynamics of materials in applied electric fields. And you know that there's this thing called the electric displacement, which is a very useful quantity I'll say more about later as well, which is just related to the electric field and the polarization. Now, oh, good, it did work. Okay, so I don't remember who I got this slide from many years ago, but I think it was Hugo Schmidt. But it's an experimental switching process in a real material. And you can see, first of all, that if you look at the picture on the right, the polarization switches as you apply an electric field. This is not showing the reverse switching here, which would be hysteretic. And this is really what defines a ferroelectric. And it's this switching process which is measured by current flow during it, which is used experimentally usually to define what the polarization is. So it goes from a negative polarization to positive polarization, and then the difference would be 2 times the polarization. And I think everybody here is familiar with that. Though if you look at the picture, you can see it's not so simple. You see it wasn't just everything flipped over. There was some complicated stuff that happened in the middle here. And that's part of, I think, the interesting thing that's going on. What is the zero is one of the questions. And that's an issue if you're trying to calculate polarization. If you're trying to calculate polarization, it's the difference between 0 and something. What is that 0? And you can see the 0 in the experiment is something complicated. I'll show some other examples later. And this is just from Nye's book, but again, just to refresh everybody's memory, we're usually thinking in real materials as finite. You know, when we're talking, certainly experimentalists, as far as I know, everybody just has finite materials in the lab. But theorists like to work with periodic infinite materials, and this is where the problem comes from. And I'm going to argue that really there still is a problem with polarization there's no problem at all in a real material, in a finite material, what the polarization is. But when you try to determine what it is from an infinite solid-state physics type calculation, there are some issues, and I think. So this is, I'm not going to go over the modern theory of polarization in any detail. There's been some slides already. Raffaella has a talk. Maybe he'll talk more about it. You can read David's book. You can read the many papers in the field. But the important thing is that it comes from the wave phase of the wave function. And what was important here is that it's related to, polarization changes are related to current. That's kind of a fundamental thing in the theory. And I have no problem with anything that's on this slide, okay? Everything here is great. It's the most amazing advance, I think. And what does this Berry's phase that comes in here, we need to think about a little bit, though, because that's where things get a little bit interesting. A Berry's phase is just a geometric phase. If you transport a vector by parallel transport on a curved surface, you see here it did this little click there. There's no way to make this thing continuous. The direction this arrow points suddenly switched there. That switch in angle is the Berry's phase. Now here's where we have a big argument, because that phase, you see, in principle every phase is moduli 2 pi. But nobody would say that this thing switched by 2 pi plus that amount, right? I mean, it just, you can see the angle there is less than 180 degrees that it switched, and it's not that angle plus 360. We deal with phases every day. You know, the Earth is a sphere, and we have the international date line, and so that lets us define what the day is. And in complex analysis, we have branch cuts all over the place in complex functions. We don't say that today is what it is the 28th or the 29th or the 30th. You know, it's modulo 1 because the Earth is a sphere, and so we can't, you know, so we can't say exactly what day it is. We decide what the phase is based on putting a branch cut in there. And that's, I think, where the argument I have comes from. So these are some of the issues that I want to discuss very briefly. Is that in the modern theory of polarization, this phase gives what's been called a polarization lattice, so that there's an indeterminacy in the polarization of 2 pi if you express it as a phase. But there's some issues with this, because this is a so-called quantum of polarization is this 2 pi, but the value of that in real units turns out to depend on the size of a supercell. And you can really not make that go, well, you can make that go away. It goes away in one dimension, and you can make it go away in more dimensions by redefining polarization, as Rafael Resta pointed out to me, making it as being P over A, where A is the transverse area. Then you can get something that doesn't depend on the size of the supercell. But there's still some issues that I'll point out anyway. And when you finally switch back to real units, it comes back again. So there's no getting rid of it completely, I don't think. A most critical thing is that the theory predicts that the polarization is not zero for some centrosymmetric or nonpolar systems. I'm going to show more about that. And then this is maybe a part that was not, I think, was not completely understood before. I found it kind of by accident, is that the polarization lattice that comes out of the theory depends on the choice of completely equivalent lattices. So for example, if you take the primitive lattice for rock salt, you get one value. If you take the conventional cubic cell for rock salt, you get a different value, even though they're mathematically equivalent lattices. So to me, that's a fundamental problem. So this is the polarization lattice. In a case where the polarization is zero in, say, a centrosymmetric case, so this would be for a centrosymmetric crystal. In a polar crystal, what happens is as you vary some parameter, the polarization changes, and you see you can get the change in polarization as you vary that parameter. That's the fundamental theory of the Berry's phase polarization. So that's fine as long as you follow some path. But the problem is really when you pick one point and just want to get the polarization at that point without considering a path. So how much do I want to talk about here? I think I've said most of this. So this is the issue with the polarization not being zero even for a centrosymmetric system. The argument is that the polarization lattice can be symmetric about zero, and then it still meets the symmetry of being centrosymmetric. So you have a bunch of lattice points of possible polarizations or polarizations, and they're symmetrically around zero, but zero is not one of the points on the lattice. So this is one of the issues that I have, because if you look at the thermodynamic theory, it says that the polarization is the derivative of the free energy of the spectrum of electric field, and that does not allow P equals zero not to be the answer for centrosymmetric case, right? And if you take rock salt, again, if you take two different cells, like I mentioned, you'll get two different types of lattices. So these are really inequivalent from each other. And so if you want to argue that one of them is correct and the other one is not correct, I think there's a problem. In fact, both of them are correct in a sense, as I'll point out. One of the most interesting our discussions of all of this, I think, is this paper and set of papers discussing these results in this. Raphael's third author here, looking at polyacetylene. So this is a one-dimensional case where you can solve the problem for both finite systems and for the infinite system. And you can show directly by Hartree-Fock calculations, for example, which they did, that there's two sets of solutions, a zero solution for the centrosymmetric chain, and a solution with this half a quantum, let's call it 1, okay, or a half. So as you go to longer and longer chains, so the chain length is on the x-axis here, polarization on the y-axis, it converges to these values that you get for the infinite system, depending on what your surface termination is. And what I want to argue is that this is, in fact, proving my point. So you don't really know the polarization of this system until you know the termination. So what you have beforehand, these two values here, I would like to call, instead of calling them the formal polarization, I would like to call them the proto-polarization, because to me, formal polarization sounds like the real thing, and if the stupid experimentalists don't get it, well, that's their problem, but the formal polarization is this number. Whenever you're talking to experimentalists, you can translate it to their language. But I want to say that this polarization lattice is kind of a potential set of polarizations depending on the termination of the crystal and the surface charge state. And but only when you specify what the surface is, then you know what the polarization is. And the other thing I want to say about this example is if you actually put a wire from one end to the other here to conduct charge from one side to the other, then you would get the zero again for the centrosymmetric case for sure. I mean, it's only when you have the open circuit conditions that there's an issue, and in typical or almost all condensed matter calculations for infinite systems, we have effectively shorted surfaces because we find a single Fermi level for the whole system essentially shorts the system at the surfaces. Okay, I don't want to, it probably takes too long to describe this, and in fact I won't. So I want to allow a little time for discussion, though David already spoke to the session chair and said make sure that the discussion period doesn't go on too long. So for Ron's crazy talk. So anyway, here's coming back to this again. I want to say that polarization in a real sample is not a lattice, and I don't think anybody would argue with that. By real sample, I mean something with surfaces. Okay, so I think people maybe have gotten confused by the literature from that. The thing that's a lattice is what I would like to call the protopolarization, and it's a very useful concept, but it has some limited utility. You have to think before you use it. I mean, it's not just a number to say is quote unquote the polarization. Like many electronic structure codes, they just print it out. Polarization is X. That's the thing I have a big problem with. Now, finally, when computing a polarization that you want to compare with experiment, one should map a path in delta P with some small change in polarization, being careful of branch cuts. And I'm going to skip this. I'm going to skip that. Here's where things get interesting and I think maybe a little bit new. So in bismuth ferrite, there's a real, and I don't have time to talk about all these words here, I'm sorry. The reason I put this up here, this is actually words from this paper, from the Neaton paper. And then it was discussed in Nicola's paper, Beginner's Guide. So I guess I need the Beginner's Guide because I'm still struggling with this. But they point out some of the things that I'm talking about here. They say possibility multiple polarization paths. So some of the things I'm talking about have already been intimated in the literature, so I can't really take credit for it. The thing is that it's possible if you don't know what zero is. So here is an example where you calculate the polarization as a function of distortion going from the ferroelectric bismuth ferrite to negative ferroelectric bismuth ferrite. And there's some path, and then you can calculate the polarization for each point along this path. The problem is, what's this path? If we choose, you notice here, this is one of these cases where zero did not give zero. So zero distortion, this is like cubic perovskite, does not give zero in any of their calculations. Instead, it's plus or minus this half a quantum. So when they map out the actual polarization and compare with experiment, they take like this number here and subtract this number for 0, and they call the difference the polarization. But if you look at the literature, the actual polarization values that are measured with bismuth ferrite are kind of all over the map. And they mostly, for bulk crystals, don't agree with this. They agree with a difference where you took this small value of polarization and subtracted 0 from it, as opposed to being this large number that has this half a quantum in it. So here's some of the experimental numbers for bulk single crystals. You see the polarization is 6 microcoulombs per centimeter squared. And for thin films, it's been measured up to 90. And that's more consistent with the number that they're getting. And sorry about the typo here. So what do we mean by polarization's a bulk property if it depends on surface termination and charging? So I think that this is something I don't want to, I'll leave that to the discussion period. But I went and looked at this system again, and I find indeed that I can make a 0 polarization case, not the half a quantum, for bismuth ferrite that's centrosymmetric, that's a perfectly good reference state too. So it seems like you can get both results, both the 0 result and the half a quantum result in a DFT calculation. So back to potassium niobate, bismuth ferrite, and sodium chloride, and I'll finish up. So I maintain that both in the centrosymmetric materials, both the 0 polarization and this half a quantum polarization lattice, they both are realizable in an electronic structure calculation. And only the P equals 0, 1 corresponds to the shorted electric field equals 0 conditions of normal DFT calculations. I'll finish up and allow a few minutes for questions. And this has been known for a long time. In fact, even when you have charged surfaces, it's known that they get pacificated in real materials, and or the charge leaks away, and in the end you end up with a 0 charge state. Potassium niobate is one of these cases that it seems like you would not get a 0 polarization when you compute the polarization, even for a rigid ion model, because the surfaces are charged. So you have like potassium and oxygen on the surface. There's no way to make that charge balance. However, people grow beautiful potassium niobate films with beautiful surfaces. So how can that be if it's so unstably charged? It must not really be charged. So I actually found, just by fooling around, that I can make a 0 polarization centrosymmetric potassium niobate by making an antiferroelectric structure. It turns out you stick this in quantum espresso, calculate the various phase polarization, you get 0. So then I said, well, and David asked me yesterday, what happens if I deform this and make it really everything on the cubic lattice? Well, it turns out if I take this doubled cell and do that, I also get 0. So just like in the sodium chloride case, I can get for cubic perovskite potassium niobate both 0 and the half a quantum lattice results within DFT. Switching, okay, I'm out of time, but, and this is not, oh, it is running. If you actually simulate a switching process in a material, what you find is it never goes to the cubic lattice. I'm out of time, so I'm going to skip that. One thing I do want to mention, though, is that whether this spontaneous polarization is measurable or not, this is something from the literature. This is from 1970, and I think it's still not explained. This is nonlinear optic coefficients versus spontaneous polarization in a whole bunch of materials. It seems to be universal that it's linear more or less in the spontaneous polarization. So that's the kind of thing maybe we should explain. I don't have time to talk about that. Okay, so maybe I'll leave a couple minutes for discussion. Thank you.
All right, can the next speaker set up while we have the questions?
So it is obvious that David and I strongly disagree with this viewpoint, and I suspect even Joel would be with us. So we started a triangular exchange of emails over several weeks, and we were unable to convince him. and so I had to figure out what is the best way, the most Cartesian, pedagogically effective way of presenting our point. And I added one slide to my presentation. I could have added even more, but this would have destroyed what I have to say on the other topics, very important. I will show again the polyacetylene calculation, so I will explain that. Now, the polycentric calculation with respect to 3D had several advantages, but with respect to the surface, the fact is that it has a zero-dimensional surface. You cannot have a metallic zero-dimensional surface, and instead, real solids are plugged by metallic surface. Then there is no depolarization field in the geometry of cylinder, because the depolarization coefficient of the cylinder are 1/2, 0. So this is ideal. That's the reason why we did. If you try to do with a slab, you don't succeed. We tried even, but you don't succeed. The surface goes metallic as soon. Now, the quantization of the polarization is something which has to be depurated by those two effects, which I regard as spurious in a sense. And so I insist polarization is a well-defined lattice, and I will show next, okay? Then instead I will say something about the two viewpoints. Actually, I'm the originator of the idea that polarization is a difference. We had this idea since several years, and then I came to the Williamsburg conference this series in '92, and finally we had a nice technical formula to compute. We were trying to implement, and Dominic Smith and David were there. They liked it, and they told me that already going back by car to Rutgers, they were reasoning about that. I came back to the Electronic Structure Conference in May. They had a poster with a theory. I went back to Lausanne, and we started working with the Berry phase all of the summer. At the end of the summer, we had the very first calculation ever of spontaneous polarization. After you have converted a phase into Coulomb per square meter, then the nuclear part, then the modulo 2 pi, at the end, our number was within 10% of what we found in Landau-Bornstein. That was the most exciting moment of my professional life. But then the second paper came out in the following year, so the one on the multivalued, because until that point was only a difference. Now, when it came out, David recalled that I was skeptical. That's true. It seemed to me rather cerebral or artificial or aesthetically not appealing. By now, in the present topological age, that's the way to present polarization. I do like that since many years. Okay, thank you anyhow.
All right, let's thank the speaker again.